Hello, this is section 7.2, trigonometric integrals. In this session, I will integrate a certain combination of trigonometric functions. Before I start integrating, let's look at some trigonometric identities that we will need in order to integrate. Let's start with the Pythagorean identity. Sine square of x plus cosine square of x, everybody knows that is equal to 1. Okay? We may take this equation and solve for sine square of x. It will be 1 minus cosine square of x, or respectively the same, we may solve for cosine square of x, 1 minus sine square of x. Just in case if we would like to rewrite sine function in terms of cosine or the other way. Also, when we have another even powers, sine to the power of 4x, we may rewrite as a sine square and another square, and sine square of x in terms of cosine, we may put here. Sine to the power of 10 of x, it will be sine square to the power of 5. And that's the sine in terms of cosine. It's just a little bit of ideas to show you how we can rewrite a sine in terms of cosine, and especially when we're dealing with the even powers. Another formula is double angle formula. Sine of 2x is defined as a 2 times sine of x cosine of x. This is the formula that we have to know. We must know. And cosine of 2x is cosine square of x minus sine square of x. Single. I did rewrite a little bit. Also, what we can do, the formula for cosine of 2x, we may rewrite in terms of sine or cosine only. I mean, when I let cosine square of x to be 1 minus sine square of x, my formula will be as follows. 1 minus 1 sine square and another sine, minus 2 sine square of x. Or the other way, if I will let the sine square of x to be 1 minus cosine square of x, then we will have the formula for cosine of 2x in terms of cosine. It will be cosine square, minus and minus, it's another cosine square, 2 cosine square of x minus 1. I mean, we may have this or this. Or simply remember cosine square of x minus sine square of x, and the green part is the Pythagorean identity. Also, I may take the double angle formula for cosine in terms of sine and in terms of cosine, and I might solve these two equations for sine square of x and cosine square of x, respectively. Subtracting 1 and dividing by 2, and of course changing the sign, and the same this one, adding 1 to both sides and dividing by 2. That means this, starting from the double angle formula, we actually get the half angle formulas. Also, nice and helpful to remember. But since we're deriving from the double angle formulas are the point. Okay. So we can see sine square of x, the sine square function could be rewrite as a function that is not square, but it's equal to 1 minus cosine of 2x over 2. Cosine square of x is 1 plus also cosine. And please notice for sine and cosine, the formula is in terms of cosine of 2x. And we have to also make sure that we understand that we can look at these formulas from the right angle. If this is x, this is always double. Okay? If this is quantity, this is double. So let's see, again, a few ideas. That's the formulas. And now, if we have sine square of 2x, that means 2x is half of this. Okay. Just to know how to apply the formulas. Sine square of 3x, 3x is half of 6x. And 5x it's half of 10x. And 10x is half of 20x. Okay, that means just make sure that we can read properly the top formulas, the half-angle formulas. Okay, what else? We also know the direct, the immediate integrals, the trigonometric integrals. Integral of sine of x dx is negative cosine of x plus the constant of integration, and integral of cosine of x is positive sine of x plus the constant of integration. Also helpful. And now let's see. That means I just said that we will just create a certain type of the trigonometric expression and we will try to integrate. That means this is the first one. We will create a product of sine of x times cosine of x. And both of them will be taken to the power of some natural numbers. Just counting numbers, 1, 2, 3, 4, 5, 6, and so on. Okay? And we will have a few cases because n and m could be even numbers or odd numbers. We know that that's the big deal, I can say, big difference, because when we have even, we like even exponents, even powers, because Pythagorean theorem or some other identities based on that are helpful. If it's odd, we have to do different things. That means, first of all, the case one, let's see how we can integrate if both of the numbers, both of the exponent n and m powers, both of them are even. Let me point the word even for you. What we will do, I type for you, we will always use the half-angle identity. Okay, this is a little bit shorter because cosine is missing. Or we may think that cosine is taken to the power of 0. Okay, sine square of x. And as I said, if you see this integral, please use half-angle formula for sine square of x. 1 minus cosine 2x over 2. And now, no problem to integrate. I will factor out 1/2. Okay, and now, integral of 1 is just x. Integral of cosine of 2x is sine of 2x over 2. Oh, times 1/2. Done. This is my final answer. Or if we like the common denominator, I did actually distribute 1/2 and I get the common denominator. But even the answer that I boxed, it's still fine. A little bit of algebra steps, it's also nice to add. Okay, now my next exercise is just cosine square of x dx. The same thing. Rewrite this using the half-angle formula. I did factor out 1/2. I mean, not factor out, I just put a constant outside because we don't have to integrate constant. And again, integral of 1 dx is x. Integral of cosine 2x, it's sine of 2x over 2. And the same process, I did distribute 1/2 and get the common denominator. But please remember, for the even exponent, we're using the half-angle formula. Okay, sine to the power of 4. We like even powers, but I don't know if we like 4. We definitely like square. And since I only see the even exponent, the sine square of x, I did rewrite using, of course, the half-angle formula. The only thing is, I still have additional square. 2 to the power of 2 is 4. That means 1/4 I can put in front. And then I have 1 minus cosine of 2x squared, which this is 1 minus cosine of 2x squared. We know where the 1/4 comes from. If I will multiply everything, FOIL, I have to square 1 minus 2 times 1 cosine of 2x and plus cosine square of 2x. And I have this. And now I have 1, no problem. I have 2 cosine of 2x, no problem for integration, but I still have trigonometric function taken to the power of even number. Again, I will use half-angle formula. I copy 1, I did copy this, and for the cosine square of 2x, I use half-angle, and we just recall that if this is 2x, it's half of this. It's the half-angle. Okay, now let's integrate. Oh, okay. Integral of 1 is x. Integral of cosine of 2x is sine of 2x over 2, but we still had 2. And now, I did divide by 2, that means we have 1/2, and cosine of 4x times 1/2. Integral of 1/2 is just 1/2 x. Integral of cosine of 4x is sine of 4x over 4 and times half. And of course, half times 1/4 is 1/8. Okay, and 1x and half x is 3/2 x. But the point is to apply the half-angle formula. The rest of them, you know how to do it. Okay, exercise number 4. Oh, now we do have a proper type that I actually start with. Sine square of x times cosine square of x. Product, both of the powers are even. We have to do this. Half-angle formula for sine square of x and half-angle formula for cosine square of x. 2 times 2 is 4. That means 1/4 I can put in front. And 1 minus cosine 2x times 1 plus cosine of 2x, it's like conjugate expression. A minus b, a plus b. To FOIL this, I will end up with a squared, b squared, and minus. That means 1 is the first quantity squared, 1. Cosine 2x squared is this, and minus. And again, I see square, I will use half-angle formula. For cosine square of 2x, if this is 2x, it's half of 4x. And what I did, I have 1 over 2 is 1/2, and negative will affect cosine of 4x and also over 2. And 1 minus 1/2, it's of course half. I mean, you can see half from that and half of cosine of 4x. And now derivative of cosine of 4x is sine of 4x over 4. And over half will be over 8. Actually, I do have this. I actually factor out 1/2. Either way, whatever algebra steps, arithmetic steps you will take at the end is fine. The main functions are important thing. Okay, that's when we know how to integrate sine x times cosine of x if they are taken to the power of even numbers. Now, the other case, the second case, is the same type of trigonometric function, sine x times cosine of x, taken to the power of n and m, but one power is odd, one power is even, or could be the other way. I don't want to point, this could be odd or even, or this could be odd or even. Doesn't matter. Because then you will think, yeah, now we need a little bit of creativity, and of course, the educated creativity. Depends which one is even, which one is odd, we will do just the U substitution. So we don't really have to really memorize this. Just looking at the problem, you will know if you will let U to be sine of x, or if you will let U to be cosine of x. Let's see. Oh, Okay, I have another slide. If both of the exponents are odd, actually, this is odd and this is odd, we may follow, you can see the same steps. U substitution, sine of x or cosine of x. And the rest of them, we will need the Pythagorean identity to rewrite, but let's put this in action. Sine square of x times cosine of x dx. That means I see 2 as an even number, of course, and cosine to the power of 1, it's the odd number. So what I will do, this one is probably really easy, because I can see right away that if I will let u to be sine of x, then I do have cosine of x dx like ready to be simplified and rewrite as a du. That means this is my du, and the entire integrand, the rest of them is in terms of sign. That means it's perfect. It's u squared du. Integral of u squared du is u cubed over 3. And now let's rewrite in terms of x, sine cube of x over 3 plus the constant c. Exercise number 6. Sine square and cosine cube times. And what we will do, in this case, I will look at the odd number, because again, we like even numbers, to be honest, right? Pythagorean identity. That means I will look at the odd exponent, odd power, and I will rewrite as a second power and 1. Okay, or I can say I will pull out one single cosine, which will be 1, cosine to the power of 1, and the remaining even. Okay, and this one I will save for my u substitution, which I am assuming that I will let u to be sine of x and du is cosine of x dx. That means I'm saving this to be du. However, in order to do this, the rest of the formula, which is this part, must be rewritten in terms of sign. If I'm planning to do the u substitution, u equals to sine of x. Sine square of x can stay, and now we have cosine square. We do have an even power. We like even powers. That's cosine square of x in terms of sign. 1 minus sine square of x. And again, this is waiting for du. Now, my entire integrand, without that box, is in terms of sign. We're ready to do this. U will be sine of x, du is in that box. Cosine x dx. U squared, 1 minus u squared. And this is my du. Let's distribute u squared times 1, u squared times u squared. Because we still have a product, we will not use the integration by parts. Okay, integral of u squared du is u cubed over 3. U to the power of 4 is u to the power of 5 over 5. Now, the last step is, in terms of u, I will put back my original function sine of x. Exercise number 7. Oh, let's say 8. 7 is missing. Okay, cosine cube of x. We see that function sine is missing, but don't worry, we can still use the same thing. I will rewrite my odd number as a 1 plus remaining even. And the 1, the single one, I am saving to be du. If this is du, if the cosine of x dx is du, then this part must be rewritten in terms of sine. Because I want derivative to be cosine, then my u must be sine of x. U is sine of x. Then my integral is just 1 minus u squared, and this is du. Integral of 1 is u, integral of u squared, it's u cubed over 3. Done. Just in terms of u, I will put back my sine function. And we can see we don't have to really memorize stuff. It's simply the U substitution and a little bit of art, creativity. Okay, another example. Oh, now, that means we know how to deal with sine of x times cosine of x. The other part of this section is another product, tangent and secant. Tangent of x to the power of m and secant of x to the power of n. Okay? And similar situation, similar idea, concept. And of course, we can see why we combining tangent and secant, because they are almost like derivatives to each other, or anti-derivatives. Okay? Because derivative of tangent of x is secant square. That's we will need two of those, secant square, or derivative of secant of x is secant times tangent. Okay, but let's start with case one for this type. We have an exponent n and m, and this will be the instruction if both of the exponents, both of them are even. Okay, if they are even, we will most likely rewrite everything in terms of tangent, and we will keep secant square at the end to be the du, which of course we will let u to be tangent. And let's see how we can do. Or maybe I do have, okay, I have another instruction slide. The same type, tangent times secant, tangent of x times secant of x, taken to the power of n and m respectively, but both of the exponents are odd, like 1, 3, 5, 7, and so on. Then we will let u to be secant, which means we have to know this, the Pythagorean identity, how to rewrite tangent square in terms of secant square. Everything must be in terms of secant, the whole integrand, except the last part, we have to keep it at the end, secant times tangent, and save it for du. Okay, let's apply. Okay, tangent square of x times secant square of x. Actually, perfect, because secant square of x is the derivative of tangent, and the whole formula outside my box is in terms of tangent. I will let u to be tangent, and it's just u squared, tangent square, and this is du. We can nicely see integral of u squared, u cubed over 3. And let's rewrite u in terms of tangent. That's the final answer. Okay, tangent x to the power of 6, secant x to the power of 4. Both even. And we remember, if it's both even, we want the entire integrand to be rewrite in terms of tangent. But if I let u to be tangent of x, derivative of u, derivative of tangent, it's secant square. That means I will look at the secant, I will pull out 2, and the remaining even, which is also 2. And I am saving this to be the derivative of tangent, which will be du. This part must be rewrite in terms of tangent. Tangent to the power of 6 is okay, but secant square of x could be rewrite as a tangent square of x plus 1. Okay, secant square of x, it's simply tangent square of x plus 1. Pythagorean identity. Okay, I think we're ready to use the u substitution. This will be u to the power of 6, u to the power of 2 plus 1, and this is my du. That's what I saved. Distributing u to the power of 6, we're getting u to the power of 8 plus u to the power of 6, and now simple integration. U to the power of 9 over 9, 7 over 7. Instead of u, let's put back tangent of x. Okay, that's what we can see. Again, I will repeat myself, it's not really new stuff, it's just to playing with these derivatives, okay, of the trigonometric function, and implement the u substitution. The right one and at the right moment. Okay, both odd. Tangent to the power of 5 of x and secant of x to the power of 3. It means this one, we will let u to be secant. If we will let u to be secant of x, derivative of secant is 1 secant times 1 tangent. It means I will pull out 1 secant and the remaining even, and I will pull out 1 tangent and the remaining even. And this is my 1 secant, 1 tangent. I'm saving this for du. Since secant must be, I will let u to be secant, then the rest of the integrand I have to rewrite in terms of secant. That means first step, let's see, maybe too fast, maybe not. Secant square is okay. Secant square will stay. Tangent square, okay, because this is like tangent to the power of 4, but I can say it's tangent square and another square, which means tangent square of x is secant square of x minus 1 and square. But it's fine, we do have extra things, but we have everything in terms of secant. I can let u to be secant of x, and this is my du derivative, secant times tangent. U squared minus 1 and extra squared, because that was 4, and u squared, and this is my du, was waiting. Let's expand this. U squared minus 1 squared is u to the power of 4 minus 2u squared plus 1. Yeah? If you like, you can do this way. You can FOIL everything, and you will get this. And we do have u squared. We have to distribute u squared because we can't really integrate product right away, directly. U to the power of 6, 2u to the power of 4, and u to the power of 2. And now the power function. U to the power of 7 over 7, u to the power of 5 over 5. We keep the constant, u to the power of 3 over 3. And instead of u, we may put back secant square of x. I mean secant of x. Okay, nice. Multiple choice, probably your exam type question, the quiz question. Evaluate the integral tangent of x, secant cube of x. That means it's the even. I will pull out 1 secant and the remaining even. That means I will have secant square of x and then secant of x, and tangent I will write here. Perfect. This is my du, and secant could be u. And I don't have to rewrite everything. It's ready for me. Secant of x, du is simply secant times tangent dx. Just u squared, and du is waiting u cube over 3, and instead of u, we can put back secant of x cube. You can see how nice and easy is the integral. And looks like option A. Okay. Evaluate the integral from 0 to pi over 4, secant to the power of 4 theta, tangent cube theta. Okay, I mean, this is again nice exam type question, but you may think, oh, let's wait a minute. 1 power is odd, 1 is even, and we don't really cover this type. But don't worry, you know the procedure, you know the algorithm. I can tell you that sometimes if 1 power is odd, 1 even, depends on the numbers, we may have a problem to integrate. But most of the time, you may apply 2 different methods. You may try the u substitution. I mean, you will definitely try the u substitution. You may try u to be tangent of x, or you may try u to be secant of x. And I can tell you, both of the methods will work. If 1 is even, 1 is odd. Okay? We know what to do when both of the even or we know what to do when both of the exponents are odd. But if this, you need a little bit of, again, it's a little bit of art. Okay, that's what I will do. What I will do, secant square, maybe I can let tangent, maybe I can let u to be tangent. Let's start from, a little bit from the middle. And then derivative of tangent is secant square theta d theta. That means I will need secant square and the remaining. I will keep tangent cube theta. I will need one. I will keep secant square and also secant square at the end. That means this is my du. That's what I decided. Okay. Since this is du, everything must be rewritten in terms of tangent. Tangent cube theta is fine, but secant square could be defined as a tangent square theta plus 1. And this is my secant square theta d theta, it's my du. Let's rewrite. This is u cube, this is u squared plus 1, and of course, that's du. Let's distribute u to the power of 5, because we, when we multiplying, we adding the exponent, and u to the power of 3. U to the power of 6 over 6, u to the power of 4 over 4. And we may try to find a new limits of integration, since we do have a new variable. When x, actually not x, when theta was 0, then u is tangent at 0, which is 0. Okay, and I can even put everywhere. If theta is pi over 4, u is tangent at theta, because I'm just using my substitution, tangent at pi over 4, which is 1. Oh, we love the limits from 0 to 1. Substituting 1, I have 1, 6 plus 1, 4. Substituting 0 is simply 0. Okay, 12 is the common denominator. That means 2 plus 3, which is 5 over 12. Again, option A. Okay, that's we can see. Don't worry if we know what to do. We know the process. Okay, and I believe this is my, I do have one more, but I can leave it maybe for you to practice. Sine squared theta, cosine cube theta. I think we did solve similar, but we didn't have a limits of integration. So you can add your unit circle. And yeah, that's everything. That means in order to integrate this, or like different integrals, of course, we always have to look at the trigonometric identities, maybe integration by parts, if you have different product, or of course, a little creativity. And my last slide just includes a few additional trigonometric integrals, formulas. Integral of tangent, but as I mentioned in my previous sessions, you may rewrite sine over cosine and use the u substitution. This one is a little bit longer. I think integration by parts is involved. This one is tricky, but you may also remember. And probably we will not even try. I mean, we can try. It's integration by parts is involved, and secant, integral of secant of x will be needed, okay, for the secant cube. Okay, that means one more time. Now, actually, it's your turn. You may try to solve every single integral one more time, okay, that I solved in this session. It will not take long, but it will give you extremely good practice, and you will get your confidence. Okay, enjoy. Thank you.